This is one of the bigger studies that I found. It was done in 2021. This will be the last one we go over, and it'll be a very brief review. So it's one of the biggest studies I found that goes over performance issues in open source projects. They went over 570 issues in 13 open source projects using Java, C, C++, and Python. Now, the premise of my argument is that we need to have programmers from junior up who are able to understand what questions to ask and provide good value judgment. And a lot of that comes with experience. And that's experience that you have to do hands-on. You cannot have an AI system give you that experience. You cannot have an autocomplete system give you that experience. You cannot have a linter give you that experience. You cannot have an automated code review system give you that experience. You cannot have automated tests give you that experience. These are things that you have to essentially go through more or less by yourself. There might be some cases where these automated systems do give you some level of proper guardrails and even experience, including like deployment systems to production systems, build tool chains, abstractions of all kinds. They can definitely have their benefits. But using an abstraction is not going to get you the experience you need to provide the right value judgment and be able to ask the right questions, even if you don't necessarily know the answers, especially as a junior. Why is it important? Software performance, I'm reading the abstract here, is a critical quality attribute that determines the success of a software system. However, practitioners lack comprehensive and holistic understanding of how real-life performance issues are caused and resolved in practice from the technical, engineering, and economic perspectives. This paper presents a large-scale empirical study of 570 real-time performance issues from 13 open-source projects from various problem domains and implemented in 3 popular programming languages, Java, C, C++, and Python. From the technical perspective, we summarize 8 general types of performance issues with corresponding root causes and resolutions that apply for all 3 languages. We also identify available tools for detecting and resolving different types of issues from the literature. In addition, we found that 27% of the 570 issues are resolved by design-level optimization, coordinated revision of a group of related source files, and their design structure. We reveal 4 typical design-level optimization patterns, including classic design patterns, change propagation, optimization clone, and parallel optimization that practitioners should be aware of in resolving performance issues. From the engineering perspective, this study analyzes how test code changes in performance optimization. We found that only 15% of the 570 performance issues involve revision of test code. In most cases, the revised test cases focus on the functional logic of the performance optimization rather than directly evaluate the performance improvement. This finding points to the potential lack of engineering standard or formally verifying performance optimization in regression testing. Finally, on the economic perspective, we analyze the return on investment of performance optimization. We found that design-level optimization usually requires more investment, but not always yields to higher performance improvement. However, developers tend to use design-level optimization when they concern about other quality attributes such as maintainability and readability. The main crux of the abstract here is that most issues are resolved by design-level optimization. That means that generally speaking, 27% of issues based on this study at least, so even if we cut it down to say like somewhere between 10 and 15% as a general rule, have to do with your cognitive ability to break a problem down and at the design level, not necessarily the code level, understand why an issue might be an issue. then deal with that at the code level. So you have to make a design level value judgment to begin approaching some of these performance problems. This is why your cognitive ability, your job as a programmer, to think about these problems and not abstract them away, especially at a cognitive level, but sometimes also at the coding level, are really critical to your job as a programmer. Because you don't even know how to approach some problems if you cannot look at them with particular aspects in mind. What does the code have to do with this? What does the design have to do with this? What does my testing have to do with this? These are all fundamental things that a lot of programmers do not know right now, and they offload that to automation systems to deal with that for them, or a library to deal with that for them. This is a problem, and that problem has manifested itself into the way that the industry is today and the way that the market is today.